Hello everyone, welcome to fourth session of this ChemCrack course series. Today we are going to see some important and interesting part of organic chemistry, that is none other than isomerism. So isomerism, it is not a separate chapter, it is linked with GOC, General Organic Chemistry, but it is very important to learn about this to solve other problems of organic chemistry, right? I know most of the students are worrying about this part, isomerism. You may miss the class, you may forget about the silly things about isomerism. In this today's session, we are going to crack that. We are going to ace the isomerism chapter. By end of this session, you'll be master in organic isomerism. Okay, so without any further delay, let's get started. First of all, what is isomerism? Iso means same, right? Merism there means parts. So isomerism means there will be some similarity, but same element in between two compounds. What are they? Let's take it out. So isomerism is broadly classified into two, that is structural and stereo. Today we are going to see both the isomerism. First, structural. It is very simple, okay? But questions can be asked from this part a lot. Structural isomerism, as the name explains, the structure varies. Same molecular formula, but different structural formula, different way of writing it, okay? So that is structural isomerism. This is further classified into main 6 types. They are chain isomerism, that is having same molecular formula but different arrangement of carbons credited. How, ma'am? Yes, we'll come to that. Chain isomerism, you can see the examples over here, that is pentane and isopentane. Pentane, you can write how many carbons? 5 carbons, CH2, CH2 and CH3. Talking about isopentane, iso means 2 CH3 group attached with 1 carbon, isn't it? So isopentane structure is CH3, CH, CH3, CH2, CH3. Right? What is the molecular formula of isopentane? 5 carbons are there. How many hydrogens? 3, 6, 7, 8, 9, 10, 11, 12. C5, H12. What about pentane? Once again 5 carbons. And how many hydrogens? 9, 9 plus 3, 12 hydrogens. Right? Same molecular formula but different way of attachment in the same chain. Chain isomerism is exhibited by only the carbon chain. No other functional groups are changing. No other substituents are changing. It's just talking about the hydrocarbons. Please be careful with that. Okay. So second part, that is position isomerism. That is having different positions of functional groups. That is very important. Different position of functional group. Let's say I'm having a functional group of alcohol which is attached in second position. CH3, CHOH, CH2, CH3. What is this? 2 butanol or butane to all. Let's say I'm attaching this functional group in third or first position, let's say. Then that will become 1 butanol, right? I just took that OH and attached to it first position. That's it. I'm not literally taking it, but the change in position of the functional group is called positional isomerism or position isomerism. That is second type. The third type is functional isomerism. What is functional group? Amines, OH, COOH, aldehydes, ketone, amides, those functional groups, right? other substituents as well. If the functional group changes, how the functional group will change? For example, here you can take alcohol and ether. Let me give you the example of, I'm going to erase this. If you are not noted, please note this down. Functional group, what is the general formula of alcohol? That is OH. What is the general formula of ether? Yes, that is ROR, right? So if I am taking alcohol, CH3, CH2, CH2, OH, this is propanol, right? Alcohol functional group. What is the molecular formula of this? Which is C3H8O, correct? If I'm writing it as an ether functional group, then that will become CH3O, CH2, CH3. What is the name of this? Methoxy ethane. Ether functional group with, what is the molecular formula? C3H8O. Same molecular formula but different functional group. That is called functional isomerism or functional group isomerism. Is it clear? Yes. Now let's move on to the confusing part, so-called confusing part, but it is not. That is metamerism. Remember this, guys, metamerism is exhibited by the functional group which is having two hands of alkyl groups. What is that, ma'am? What is two hands of alkyl group? Let's say I am considering alcohol. What is the general formula? ROH. Only one R group is attached with that. If I am considering ether, ROR, two functional groups are there. Oxygen is attached with two alkyl groups. That is having two hands holding the alkyl group, right? Metamerism only exhibited by the compounds like this. I can give you another example like ketone. Right? So metamerism is exhibited by these kind of groups, not for RH or RCOOH or RCHO, RNH2, nothing. Only the functional group which are having two hands. Is it clear? Most of the students do mistake in this part, particularly metamerism. I don't know why, but hope this is clear now. What is metamerism? Once again, that is having same functional, the molecular formula, but different alkyl group attached. Say for example, here I am having either as an example CH3O, CH2, CH2, CH3. Okay. Another isomer of same compound is CH3, CH2O, CH2, CH3. The molecular formula is same, C4 C4H8 plus 3 11 3 14 O, C4H14O, H14 H10O. Similarly here also that is C4H10O. Okay, but the alkyl groups attached with this functional group is getting differed. Here I am having methyl, this side I am having propyl. Here I am having ethyl, another side I am having ethyl. Okay, so please be careful with that. Next functional group, that is tautomerism. What is tautomerism? I am explaining to you with an example. Tautomerism is a reversible thing. Okay, a molecule can go with product side or reactant side like an equilibrium. Okay, say for example, if I am having acetone, CH3, CO, CH3, and if I am having propane 2-ol, how many carbons? 3 carbons must be there. Propane all. Okay, so how many carbons? 3 carbons. C3H6O. This is also C3H6O, right? Same molecular formula once again. But what happened over here? The shift of hydrogen. This maintains an equilibrium. This is keto and this is enol. The shift of hydrogen happened over there. So it will get cleaved, O becomes negative, so hydrogen get attached with oxygen. So keto-enol tautomerism. Similarly, we have nitro-acinitro tautomerism. But mostly they will be asking about keto-enol tautomerism. You must have seen this in mechanism part. Okay. The last type of structural isomerism is ring chain isomerism. That is very, very simple. If I'm writing it in chain, I can write it in ring model also. How? Let's say I'm taking propene. Cyclopropane. CH2, CH2, CH2. How many carbons? 3 carbons, 6 oxygen. Right? How many carbons over here? 3 carbons. Sorry, talking about hydrogens. How many hydrogens? 6 hydrogen. So C3H6, same molecular formula. I'm writing this is ring and this is chain. Sorry. The next part, that is very simple isomerism type, that is ring chain isomerism. Ring. For example, if I'm writing cyclopropane, CH2, 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 C3H6. If I'm writing propene, CH2 double bond, CH, CH3. The molecular formula is C3H6. Same molecular formula I have written as ring structure and this is chain. Okay. So this is ring chain isomerism. The questions can be asked from this part for this year. So please be prepared. What is isomerism? That is very, very important point to be noted here is where you will get confused. That is metamerism is sorted. Functional group isomerism is sorted. Positional isomerism, that is very, very, very important. It's meant for functional groups only. Metamerism is meant for the functional group which are having 2 sides to hold their alkyls. Okay, so hope this is clear. If you have any doubt in isomerism, please let us know. We explain it in detail as a separate video. Now let's move on. The next part of isomerism is stereoisomerism. Stereo is not like sound. Stereoisomerism is having different spatial arrangement. Where that is arranged. Structural isomerism is how that is arranged. This is where that is arranged. This is having the further classification of conformational and configurational. Guys, please be aware, conformations and configurations are entirely different. Conformations are the one which are having different spatial arrangement due to rotation about sigma bond. Okay, so let's see this in detail. First, configurational isomerism. Here, I am going to take geometrical isomerism first. What is geometrical isomerism? It is having restricted rotation. It is having restricted rotation. What is restricted rotation? Let's say I am having double bond. CH2, CH2. Can I rotate this molecule? it possible? There is lots of strain. There will be a restriction to rotate this molecule, isn't it? I'm not talking about the rotation in this wise. I'm just talking about the rotation over here. Right? So that restricted rotation is about geometrical isomerism. Let's have some examples of geometrical isomerism so that you will be very clear about that. For example, if I'm taking C double bond C, A, and this is B, and this side I'm having A and B. Okay. Can I rotate it in this way to form B, A, A, B? Guys, please be aware, I'm not talking about rotating the entire molecule. I'm just talking about rotating one side. Okay. So can I get this molecule by rotation? Obviously not, right? Because the rotation is restricted because of the double bond. So this is not possible, which makes this is a different molecule and B is a different molecule, right? So what would be the name of these? Let's name this depend on the attachments. So here we have two type of configurations. The first one is cis-trans isomerism. This is if the two similar groups are on the same side of restricted rotation. Then the configuration is cis. Say for example, if I'm taking a molecule of this, two groups are on the same side, then that is cis. If that is an opposite side, what that is mean? Then that is trans. Then that will be considered as trans. As simple as that. I'm having a double bond. I'm having a group, similar groups, which are attached on the same side, then that is cis. If that is attached on the opposite side, then that becomes trans. Okay? Similar group, note it down. What about the other classification? That is EZ. EZ isomerism. What is the difference between these two? Once again, this is also deals with the restricted rotation. This is also deals with the double bonds and where the restricted rotation are possible. Here, the important point is seniority of groups. Seniority of groups. What is seniority of groups? Say for example, if I am having Cl, I, H and Br. Let's take one carbon and consider these two substituents, hydrogen and bromine. Among these two, which is having highest atomic number? Of course, bromine. So I'm ranking it 1. Hydrogen will get second rank. Considering another carbon, Cl and I, which is having highest atomic number? Obviously, iodine. So first rank goes to iodine and the second rank goes to chlorine, right? So depend on this seniority of the groups. If that is positioned in the same side, then that is Z. You can remember it like same. This is also having the same sound. Z is also having the same sound. Okay, Z. Just remember it like that. So if that is on the same side, then that is Z. If that is have on the opposite side, the high priority groups are high priority groups are on the opposite side, then that is E. This is 1 and this is 1, which is on the opposite side. Then that is E. E for opposite side. Is it clear up to this part? Cis trans E Z. Okay. Is there only one way for mentioning geometrical isomerism? None other molecules are having any restricted rotations? No. There are some molecules which are having restricted rotation. The most important one is rings. For example, if I am taking cyclopropane that is attached with the substituents A and B, how it will undergo rotation? How that will undergo rotation? It's not possible, correct? So in that case, how it will form this kind of molecule B, A and A, B? This is not at all possible, which means that this is having restricted rotation. So this can also be possible in geometrical isomerism. Other than this, one ring system which is having a double bond or which is having lone pairs of double bond, this system is also possible. Okay, mostly they will be asking questions from rings and double bond. Hope this is clear as far as now. Then we are moving to next part, that is RS notations. Naming R and S for molecules. We are naming it under the rules which is called can in whole prolonged rule, that is CIP rule. Okay, what this rule says? The first rule is that the group with the first atom having high atomic number is the senior. High atomic number, what we have saw in other examples also. High atomic number, that is priority 1. That is first rule. The second rule is higher mass isotope. Let's say I'm having isotopes for let's say hydrogen and deuterium, hydrogen and tritium, deuterium and tritium. So high masses, high mass isotope, that is senior, that gets more priority. Okay. The third rule is if I'm having a situation of the first atom of a molecule is same, CH3, CH2, the carbon which is same, the atomic number becomes same. In that case, I have to go to second atom. First atom same, then we have to move to second atom. Fourth rule, groups containing double and triple bonds are assigned seniority as both atoms are duplicated or triplicated of that. If I'm having double bonds, which means that I'm having two molecules of same. If I'm having double bond CH2, then I should consider that as I'm having two CH2 over there. If I'm having triple bond over there, triple bond CH, then I should consider that as three molecules of CH is present over there. Depend on that, I have to give the seniority. And rule number 5 is bond pair is more senior to lone pair. Bond pair is senior or gets high priority than lone pair. Don't be scared of seeing these rules. It's just very, very simple. While solving the problem, while solving these examples, you will get to know. And there is a special rule I'll let you know while solving problem. Now, solve this problem to get to know these 5 rules and secret rule better. Before that, I would like to let you know R is for clockwise and S is for anti-clockwise. Okay, why I'm talking about the rotation now? Let's take it out. Here I'm having the first example. Hydrogen, COOH, CH3Br and Cl. So which will get more priority? Obviously, the first priority will go to Cl. Considering COOH and CH2Br, which will get more priority? Both are starts with carbon. So we have to look for second atom. That is rule 3 says, right? So second atom here, that is what? Here the second atom is bromine and hydrogen. Don't misunderstood, that is hydrogen. Don't do this blender over there. That is Br. Because you can see this is attached like this. Carbon attached with Br. So you can take Br as a second atom attached over here. Okay. So what about here? COOH. Carbon is attached with double bond O and bond OH. Right? So the second priority goes to CH2Br. So the third priority is carboxyl group and the fourth priority is hydrogen. Now one rule you have to remember, that is you are going to find the path, whether that is clockwise or anti-clockwise. In the journey you have to remember one thing, you have to go via 4, not via 3. Okay. If 2 is not available, here 2 is readily available nearby, so you can go by this way to reach 1. Whether that is clockwise or anti-clockwise. Is it clockwise or anti-clockwise? This is clockwise, so it becomes R, right? So let's go to second example. Once again the priority groups become same because I just took a same example in different position, but the groups are same, so the priority order will be same. Will that change the notation? Let's see. Cl, CH2Br. Okay, so I can go like this. Is it clockwise or anti-clockwise? It is clockwise. It should be R, but it is not. Why? There comes the sixth rule. Sixth rule says that if there is a fourth priority group on front of you or above the plane, you have to reverse the notation. So I can simply write the least priority group must be behind the plane or far from you. Ma'am, how to find above the plane or behind the plane over here in this kind of Fisher projection? In that case, you can take hydrogen must be in vertical position. Okay, hydrogen must be in vertical position. I mean the least priority group must be in vertical position. Here that is in horizontal position. So I have to just reverse the notation. It becomes yes. And the third example over here, that is which is having 2 carbon system. If I'm considering the first carbon, which is green color, you have to take this group as a single group like we took for COOH. Okay, so in that case, which will get more priority? COOH or nitrogen group? Obviously nitrogen, because nitrogen atomic number is 7, carbon atomic number is 6. So first priority goes for nitrogen, second priority goes to COOH, third priority is for the group below, and the fourth priority is hydrogen. So least priority group must be in vertical position, Here that is not same, so I have to just do the opposite. Before that I have to find the clockwise or anti-clockwise, right? So this is clockwise or anti-clockwise. This is clockwise. Clockwise must be R, but I have to use the reverse rule, so this becomes yes. So let's take another number of degrees of rotation observed when the compound is passing the plane polarized light. Okay, how much it is showing that rotation. Here we have the formula for that. Specific rotation alpha, which is equal to theta divided by L into C. Here L stands for path length and C stands for concentration. Theta is observed angle of rotation. Okay. Sometimes they will give you the values of path length, concentration and the rotation angle. They'll ask you to find the specific rotation. So please be prepared for that. So this kind of question can be asked. And now let's move on to another important part, that is chirality. What is chirality? A compound which is not superimposable to its mirror image. That is called chiral. Non-superimposable to mirror image. That is chiral. Okay. While a compound is superimposable to that mirror image, then that is called achiral. If that is superimposable, then becomes achiral. So how we can find that? We can find the chiral center. So what is chiral center is that? A compound in which carbon is attached with 4 different groups, which is lacking for symmetry, is called chiral carbon or asymmetric carbon. Lack of symmetry. We do have plane symmetry, plane of symmetry, axis of symmetry, and center of symmetry. Which lacks for symmetry, then that is asymmetric carbon, and if that is attached with 4 different groups, it is attached with 4 different groups. I'm talking about carbon, that's why I'm mentioning 4. 4 different groups, then that is chiral center or asymmetric center. Flakes of symmetry means asymmetric center, attached with 4 different groups means chiral center. We'll see the example. For example, if I'm taking a carbon that is having 4 different groups, this is chiral carbon, which can be denoted by the symbol star. Okay. Similarly, the asymmetric carbon can be denoted by the symbol star. Now we are moving on to the another important part, that is different type of writing a molecule. Different type of projections. Projection formula. What are the different types of writing a molecule? For example, we have wedge dash. We have Fisher projection. We have Newman projection. We have Sohas projection. These are different methods of writing a compound. First, what is wedge dash? Wedge dash is writing it with the 3-dimensional system of, let me write it here, carbon. What are these? So here the simple dash refers for that substituent is in the plane. It's on the surface, is in the plane. If that is denoted by like this, like wedge or dotted lines, then that is behind the plane or far from your way. Behind the plane. If that is mentioned as solid wedge, the former one is a dashed wedge, this is solid wedge, then that is above the plane, it's towards you, that is wedge dash. Talking about the next projection, that is fissure. Fissure projection of writing is writing as a cross. For example, we saw that in RS notation as well, like this. Here how we can find it out whether that is above the plane or behind the plane. So which can be denoted as like this. The horizontal ones are above the plane and the vertical ones are below the plane, which is equal to this. G, C, O, O, H and H. Okay, that is fissure projection. Moving on to the next part, that is Saha's projection. Saha's projection is a molecule viewed slightly above, like top angle view, like this, like this. This is kind of a top angle view of the carbon attached with the substituent. The final projection, that is Newman projection. Newman projection, which is like man standing over here, which represents the front carbon and the back carbon, like this. Here I am having two carbons. What are they? The first one, let me take the dot, the green one, which is represented by a dot, and I'm taking another one as in pink, which is here, that is round, right? So the dot one, the point, represents the group attached with near to the eye. Okay, it's towards you. The dot is towards you. And the circle represents away from you. Behind plane is away from you. That is rear carbon. Okay, so that is Newman projection. How we can convert this? How we can do the conversions of one projection formula to another one? If you want, we'll do that in detail. Now I'm giving you just a simple example of this. For example, if I'm taking 2,3 dimethyl butane. Butane, so 4 carbons must be there. 2,3 dimethyl. So remaining hydrogens. For this texture, we are going to write all other projection formula. First, let's start with wedge and dash. Here I am having 2 carbons. Okay. So let's say I am having hydrogen on the behind the plane, 1 CH3, it's on solid wedge, which is towards you, and for another carbon, hydrogen is towards you, CH3, it's away from you, and 1 is on the plane. So I took wedge dash like this. Okay, depend on that how we can write it for other projection formulas. Okay, I'm considering these two carbons as a main carbon, front and rear carbons. So now let's go to the second projection. I have the lines. So this and this carbon, one carbon is attached with two CH3s and one hydrogen. Okay. So here I'm having CH3. So CH3 with CH3 right side I'm having hydrogen, left side I'm having another CH3. Note it down. These are opposite to each other. The wedges, solid wedges are opposite to each other. So how we have to write the opposite pair? That is one CH3 to another CH3 is just opposite. So CH3 opposite side, and then to that CH3 I'm having hydrogen and another dashed wedge CH3. Now let's go to the third projection formula. Here I'm considering CH3, this CH3 and another CH3 must be on the same side, or I can write it in the opposite side if I am writing like this. Both the CH3s are opposite, hydrogen are opposite. So because while doing the rotation, I can get it on the same side. That will equals to this direction. Right? Clear? So now let's see Sawhorse projection also. So front and rear carbon. So front carbon, that is dot. So I'm taking CH3, this guy, and then CH3 on left side, hydrogen on right side. And if I'm considering the rear carbon, that is circle. So CH3 goes on the top and another CH3 on the right, hydrogen on the left. Okay, so this is as simple as that. I will tell you, you can work on 2-bromo, 2-chloro-butane, and let me know if you are facing any problem while doing 4 other projections for this compound. What is optical isomerism? We all know it comes under the category of stereoisomerism. Stereo means difference in spatial arrangement, right? Optical isomerism is a form of stereoisomerism where the molecules have identical molecular formulas and bond connectivity but differ in 3-dimensional spatial arrangement. Most importantly, it results in non-superimposable mirror image. Okay, so if you are matching those mirror image, it will not match. That is what the non-superimposable mirror image is. Okay, so that is what optical isomerism. The molecules are the compounds which exhibit this property. Those are called optical isomers. Okay, so without getting much detail about it, I just want to give you the terms we are using to explain this optical isomerism. Okay, the first term, that is chiral carbon. Chiral carbon, asymmetric center. These two are the different words. Chiral carbon are the carbon atom which is attached with 4 different molecules or atoms. Say for example, I'm having carbon attached with hydrogen, iodine, fluorine, and another side CH3. 4 different groups are attached with carbon, that is chiral carbon. This is mentioned as star, asterisk symbol. Okay, and this is called stereo center or asymmetric center. More importantly, asymmetric means if the carbon or the compound is lacks of symmetry. There are different types of symmetry: plane of symmetry, axis of symmetry, center of symmetry. We are going to see about that. Okay, if a compound lacks these symmetrical property, then that become asymmetric. Those are called asymmetric carbon or asymmetric center. Okay, here this carbon is asymmetric carbon. Our next part is that optical isomers. Optical isomers are the molecules which can rotate the plane polarized light. What is plane polarized light? That is our normal light, white light, which is having vertical and horizontal waves in it. Okay, so which will be looking like, let's say this is the plane. It would be better if you are imagining it in three-dimensional way. The vertical lines and the horizontal waves as well in case of our normal light. But in case of plane polarized light, we are producing it through passing the white light into nickel prism and polarizer to make it as a singly arranged waves. Waves are in only one direction. Okay, that is plane polarized light. So if an isomer exhibits optical isomerism, then it can rotate the plane polarized light either clockwise or anti-clockwise. If that is rotating in clockwise, then that is called d-isomer, also denoted as plus symbol. Okay, if that is rotating that as an anti-clockwise, then that is L-isomer, denoted by minus symbol. Okay, so which can rotate plane polarized light to clockwise, that is d-isomer, which can rotate plane polarized light to anti-clockwise, that is L-isomer. This much clear? Yes. I said the word rotate. So rotation means the angle changes, right? So how much it is getting rotated? Let's say I'm using a molecule tartaric acid or any optically active molecule. How much rotation is happening, either clockwise or anti-clockwise? That rotation we are talking about here in case of specific rotation. It measures the optical activity. And how it is calculated? Specific rotation is alpha, and this is calculated by alpha L into C into 100. Alpha by L into C into 100. Here alpha is observed rotation when we are passing the molecule into plane polarized light, and L is the path length of in decimeters. C is the concentration of the solution. Okay, this rotation is observed using a polarimeter, that instrument, and it can be of positive, dextrorotatory or levorotatory. This kind of question can be asked to apply this formula. They will give you observed rotation, path length, concentration and all. They can ask you find the specific rotation. Okay, so that kind of question can be asked. Let's move on to the next part. That is types of stereoisomers. Types of stereoisomers, we talked about optical isomers, we talked about conformations. Here, enantiomers and diastereomers. What are these? These are very simple. That if that is an enantiomer, then the molecules are, the mirror image of that molecule will be non-superimposable. Non-superimposable mirror images are called enantiomers. They'll have identical physical properties. Physical property means color, smell, what we can observe it without doing a reaction, and those parts of physical properties, they will have identical physical properties except the rotation of plane polarized light. It can be of D or it can be of L. And interaction with their other chiral molecules. How it will interact with other molecules. What is this word chiral over here? Chiral means the same. I told you, right? Stereo center or chiral center. Chiral means a carbon which is having 4 different groups attached to it. And enantiomers will have equal and opposite specific rotations. D and L pair are considered as enantiomers, but they should be of mirror image and non-superimposable. Talking about diastereomers. Diastereomers are the stereoisomers which are not mirror images and not superimposable also. They are neither mirror images nor superimposable. They'll have different and chemical properties entirely and can occur in molecules with multiple stereocenters. They can have multiple, more than one stereocenters. We'll see the example. For example, if I am taking a molecule like this, HCl, HCl, C2H5. What about the mirror image of this molecule? Once again, this will have CH3, C2H5 will be on the same position. Cl will come here, H will be here, Cl and H. These are mirror images, but is it superimposable or non-superimposable? For example, if I'm taking this molecule and trying to match with the original one, is that matching? No. Cl and hydrogen are in different positions, right? So, which means that it is non-superimposable. Okay, so these two are enantiomers. Enantiomers. It can be of D and L. Talking about diastereomers. For example, if I am taking a molecule, let's say I'm taking the same molecule and a pair of this diastereomer will be there shouldn't be a mirror image, right? So it can be like this. So these are not mirror images, and as well as these are not superimposable also. They are diastereomeric pairs. Okay, if examiner gives you a molecule, check with these conditions and put the right answer whether that is enantiomer or diastereomer. Now we are going to see the next part, that is elements of symmetry. We have different symmetric properties. As I told you earlier, what does asymmetric center means? If that lacks of symmetric property, then that is asymmetric center, right? Asymmetric carbon. What are those symmetric properties? In general, we have these three important symmetric properties, that is plane of symmetry, center of symmetry and axis of symmetry. Plane of symmetry is very simple. Let's say I'm taking a molecule which is having two stereogenic center, let's say, and I'm having these H. So from here, these two are mirror images to each other, isn't it? So this is mirror image. So both the sides we can see the same molecule. That is plane of symmetry. If we divide the molecule into two identical halves, the mirror image relationship between there in this compound, right? This is plane of symmetry. Although the four different groups are attached to the carbon, since that is having a plane of symmetry, this compound is not optically active. Okay, and the second one is center of symmetry. Center of symmetry means from the middle line, how the symmetry occurs. For example, if I'm taking a molecule like this, the simple molecule, let's say I'm taking a simple CO2 molecule, simple CH2CCH2. Okay, so here I'm having central carbon, and both the sides from this point I'm finding the same compound, same molecule attached to it, and another side also I'm finding the same molecule. So which means that is having center of symmetry. Okay, so that is one symmetric property. And the third one, that is axis of symmetry, means if I'm rotating one side of a molecule, I should get the same thing. Let's say the simple molecule, I would say that is H2O. Okay, let's say I'm HA and this is HB. I'm naming it, these hydrogens. So I'm rotating it on one side. It will become HB and HA, isn't it? Once again, I'm rotating it. I'll be getting the same molecule again. So the rotational axis that produces the identical arrangement multiple times per 360-degree rotation, then that is having axis of symmetry. Why these are important means, depend on this, we will find whether the compound is optically active or not, whether the compound exhibit optical isomerism or not. Okay, so this is some basic thing. Mostly they will be asking questions from plane of symmetry. We applied this concept in another compound that is called meso compounds. Meso compounds are the one which are having chiral center, but that is optically inactive because of the cancellation of optical activity, that is because of plane of symmetry. Okay, the same example as here, I am taking tartaric acid. So this is having a plane of symmetry, right? That's why it makes this compound optically inactive. That is very much important. Meso compounds are optically inactive, although they are having chiral centers. But what if that is having odd number of chiral center? Optically activity may come, but this is common where the even number of chiral centers are there, even number of stereo centers are there. Okay, and finally another term, that is racemic mixture. Racemic mixture is nothing but, we talked about D and L isomer, which can rotate clockwise, that is D, and which can rotate anti-clockwise, that is L, LIBO and extrorotatory, right? So if a compound that consists of both the mixtures, both the compound or both the isomers together, that mixture is called racemic mixture, but that should be of equal amount. Let's say if I'm having 50% of D isomer, then I should have 50% of L isomer. The equimolar mixture of D and L isomers are called racemic mixture. Okay, and what will happen to that optical activity means, it will become optically inactive because of external compensation, which means D isomer is plus isomer that rotates on one side, L isomer is minus isomer that rotates the plane polarized light to another side, which will cancel out each other, right? Racemic mixtures are optically inactive because of external compensation. Meso compounds are optically inactive because of internal compensation. Clear? Now let's move on to how to find number of optically active compounds or optically active isomers in a given molecular formula or given structure. Okay, there are three different formulas we have, these different possibilities we have. The first one is unsymmetrical molecule. It is not at all having any symmetry in it. No plane of symmetry, no center of symmetry, no axis of symmetry. Then you can use the formula of 2 to the power n. N refers to chiral center. It can be of any number of carbons. 2 chiral center, 3 chiral center, 10 chiral center, it can be of anything. So number of optically active isomers become 2 to the power n. And out of this, which is meso form, we said that is not possible over here, they are unsymmetrical. And the racemic mixture becomes A by 2, which means if I am getting 10 optically active isomers means 5 will be racemic mixtures. The total isomers are A plus M, that is 2 to the power n only. Okay, the second case, that is symmetrical molecules with even number of asymmetric carbon. Even number means 1, 3, 5, 7, etc. In that case, you have to use the formula, the two optically active isomers are 2 to the power n minus 1. Once again, n is for chiral center. The mesoforms will be 2 to the power n by 2 minus 1. and the racemic mixtures, which is A by 2, total isomer A plus M, optically active isomer plus mesoforms. And finally, the third category, that is symmetric molecule with odd number of asymmetric carbons, like 2, 4, 6, 8, and etc. In that case, optically active isomers would be 2 to the power minus n minus 1 minus 2 to the power n by 2 minus 1 by 2. Okay, here this part belongs to meso compound, and total isomers become 2 to the power n minus 1. Okay, so kindly take the screenshot of these formulas. This will be very useful while you are solving this kind of problems. Okay, then we are moving on to optical activity without asymmetric carbon. You said it should have a chiral carbon, it should have an asymmetric center, but how a compound can exhibit optical activity without having those centers? Yes, that is possible. Those molecules are allenes, spiranes, biphenyl with restricted rotation, some metal complexes. Here, these names are important. Okay, I'll give you the structure. So if an examiner is giving you the structure, then you won't be able to answer this question if I'm not giving you the structure. The first one is allenes. You can see it is having CCC in the middle, 3 carbons, and A and B, the different molecules or atoms are attached. Here, how it becomes optically active? The first thing is, it is having a double bond in between, and these double bonds are arranged in the way perpendicular to each other. The 3-dimensional way, I should write it like this. Can imagine this carbon is perpendicular, it's towards you. This B is away from you, A is towards you, and these two are in the plane. It takes out a different 3D arrangement. That's what the optical isomers are, right? So that makes allenes with odd number of carbons become optically active. What will happen to even number of carbons in allenes? Then that will become optically inactive, because that will get cancelled out each other, compensation happens, that becomes optically inactive. Okay, the next example is spiranes. Spiranes are nothing but replacing the double bond with the spiral structures, like replacing it with this kind of structures. And biphenyls with restricted rotation. Say for example, here I am having biphenyl CH2 S double bond O, another phenyl ring. So these are having biphenyls, but the carbon that becomes optically active because of the tetrahedron shape, because the attached groups are different. Some metal complexes, we'll see that in coordination chemistry chapter. Point to be noted here is allenes, spiranes and biphenyls are optically active even though that is not having asymmetric carbon. Then we came to the last part of this session, that is conformational analysis or conformational isomerism. Here I just want to give you the important points to be noted. The first of all, conformations is due to the rotation around the single bonds. There is no work for the double bond, triple bond sections. Only the rotation due to the single bonds. Okay. Say for example, I am taking ethane. CH3, CH3. Is there any double bond? No. Is there any possible rotations? Yes. I would like to represent it like this, with This is front carbon and circle is rear carbon. We saw that in last class. Sorry. H, H, H. There are two types of arrangements over here for this conformations. I mean, there are two types of conformations we can have for ethane. One is that staggered, another one is eclipsed. This conformation is called staggered, and the eclipsed will be look like this, which is having the bond angle or dihedral angle between the atoms will be very, very less when we are compared to staggered. Out of these, which will be more stable? Staggered will be more stable than eclipsed. Okay, because in case of eclipse, the repulsion can happen, which makes it less stable than the other conformation. Similarly, you can draw that for butane as well. Butane, CH3, CH2, CH2, CH3. If you want a detailed analysis of butane, let us know. Here the front and rear carbons to be taken in these two carbons. Okay. The one of those conformations will be looking like this. Here, for the staggered and eclipsed, we do have other arrangements as well. I'll give you the most stable conformation of butane, that is anti-conformation. Both the CH3 groups are opposite to each other. The anti-conformation, which is more stable in case of butane. Other conformations are fully eclipsed and gauge, partially eclipsed. Those will be there, but out of those, anti is more stable because both the CH3 groups are opposite to each other or anti to each other, so the repulsion or the dihedral angle will be very less, which makes it much more stable. Then cyclohexane. Cyclohexane means what? Ring which is having 6 carbons, right? So this type of arrangement, this type of structure for cyclohexane is much more congested, much more strained. For that, we can write it in different way. Out of one way is this, which is called boat and chair. This is chair and this is boat. Out of these two, which is more stable? Chair conformation becomes much more stable than boat conformation because it eliminates the axial and equatorial bond strain and repulsion, and those stuffs are there. This part we can go in detail, but it will take more time. It involves lots of concept. So I want to make it short. I just want to tell you, chair conformation is much more stable than the boat conformation. That those kind of questions only we can expect from JEE Main and NEET. Okay. So by this, we just finished the theory part. Let's see whatever we have learned, can we solve those questions through this? Okay. So the first question is about which of the following compounds will exhibit geometrical isomerism? The option A, 2-phenyl 1-butene. Quickly we'll draw the structure. 1-butene and 2-phenyl. And 1,1 diphenyl 1-propene. This is A. B is 1-propene 1,1 diphenyl. and C is 1-phenyl butene. 1-phenyl 2-butene. 1-phenyl 2-butene, and D, that is 3-phenyl 1-butene. 3-phenyl 1-butene. Okay, so out of this, which can exhibit geometrical isomerism? You can see it should have two different groups attached with single carbon, and it should have a double bond in it, right? Let's take option A, that is having 2 hydrogens over here. That makes it optically, it is not exhibiting geometrical isomerism. And if I'm talking about these phenyl group, then surely that is not. And what about this one? Yes, it can. So let me write it in this way. Carbon which is attached with 1 hydrogen, another CH2 phenyl double bond, another carbon with hydrogen and CH3. So this can exhibit geometrical isomerism. What about option D? That is not, because of 2 hydrogens over there. So the right answer is option C. These are previous year questions and anticipated questions for this year. Okay. Then number of structural isomers for C6H14. Structural isomers. So first write the molecule and then find out what are the different ways we can write it for this. Okay, so this is number 1, and number 2 is, I can put CH3 in the middle. CH, CH3, CH2, CH2, CH3. Third configuration, I can write it with isomers. I can write as CH3, CH3, CH2, CH3. And the fourth possibility can be CH3, CH3, CH, CH3, CH3, and the fifth possibility, that is CH3, CH2, CH3, CH2, CH3, H. Is it possible that the name of this compound will be 1, 2, 3, 4, 5. So second position I'm having, third position I'm having methyl. Here I'm having it in second position. Here 2, 2. Here I'm having it in 2, 3. So these are the 5 possibilities I can write for structural isomers of C6H14. Let's move on to this question, which is asking about absolute configuration of this structure. Here I'm having 2 carbons. Let's say this is 2 and this is 3, because we should start naming it from functional group. Okay, so let's do the absolute configuration of carbon 2. That is, it starts from OH, then it goes to Cl, then COOH, finally hydrogen. So hydrogen, which is in above the plane, which is in horizontal position, we have to do the reverse of whatever the result we are getting. So first of all, 1, 2, 3, 4. So which makes it clockwise and R. So I have to make it as yes. So 2, yes. Then the third one, I'm numbering it different color, 1, and this becomes 2, this is 3, and hydrogen becomes 4. Once again I have to do the reversal. This time this is going 1 and 2, that is anti-clockwise, which is yes. Doing the reversal, that becomes R. So 3 R, 2 yes, that is the answer. Then next question. Acetone and propanol are what kind of isomers? Acetone, which is having keto functional group, propanol, that is aldehyde functional groups. So these are functional isomers. Then number of optical isomers of the compound. CH3, CHBr, CHBr, COOH. So how many optical isomers this compound is having? Obviously this is not having any meso compound. Okay, so this is having 2 chiral centers. So optical 2 chiral center, and is it symmetric? No, is it not? It is asymmetric. So apply the formula 2 to the power n. So n here is 2. So which makes the answer D. Let's solve this question. Total number of acyclic structural isomer possible for the compound of molecular formula C4H10O. Okay, we should not include any rings. Okay, so let's start writing it. This is 4 carbon system. So CH3, CH2, CH2, CH2OH. So number of carbons are 4, number of hydrogens becomes 7, 7 plus 3, 10. And the second way of writing it, which is, you can put the functional group in second position. CH2, CH3. The third way, it's giving the substituent at different position. CH2, OH. Fourth way, I can write it in the way of 3-degree carbon. And the fifth way of writing it will become the different functional group. Is it possible? We know the functional isomer of alcohol is ether. So let's try out that way. CH3, CH2, OCH2, CH3. How many carbons? 4. How many hydrogens? 10. And 1 oxygen. Okay. The next way, let me write the different isomer of the ether. It is the metamer of this ether. And the another metamer is, kindly check number of carbons and hydrogens are sorted. Yes. So these are the possible acyclic without any ring. I can write the structural isomers of this molecular formula, that is 7. Now let's move on to the next question, that is asking for meso compounds do not show optical activity is because we know not very well, right? They do not contain chiral carbons. Yes, they do have. They have non-superimposable mirror images. They contain plane of symmetry. They do not contain plane of symmetry. They contain plane of symmetry. So that is the answer for this question. Optically active molecule is among these 4. So let's analyze it one by one. Is it optically active? No. This is having plane of symmetry. This becomes meso compound. So this is not. And what about this? This is also not because of plane of symmetry. And what about this one? Here you can see COOH and COOMe. So which makes it different? And final compound, that is also exhibit optical inactivity. So the answer to this question is option C. What I tell you is do as many as problems you can, try to do more questions, come up with different ideas to how to solve the questions. That will give you deeper understanding about the concept rather than studying the concept. Okay, so practice more because practice makes a man perfect.